Namaskar. I am Rajababu, Program Director AD, DRDO, who has participated in Mission Shakti. First, before I start my talk, I would like to take this opportunity to thank Vigyan Bharati AP chapter and Sri Shastri Garu in particular for giving me this opportunity to share my experiences on the Mission Shakti, one of the most challenging mission through which India could demonstrate to the world its technical capabilities. There were many challenges in this mission. I'll speak during my course of talk. First, before we start the talk about specifically about Mission Shakti, I thought it is appropriate to brief about the enabling technologies. And since most of the participants are working in the area of science and technology, I thought it will be apt to bring out how the technology has transformed especially defense, because basically we're working on defense technologies and how these technologies are used for the defense of the nation. If you see, initially the warfare was limited to very primitive technologies, and the warfare was confined to the individuals. That means if a person is there, he is fighting a war alone, be it be soldier on the field, or a pilot in the aircraft, or a submarine in a submarine. He is with the platform, and then he is all alone with the platform. Now today the concept is changing. With availability of communication and networking, today we are talking about network-centric warfare. That means we are able to control many sensors, many resources in a central place far away from the battlefield. How is it possible? It is possible because of networking. We network all the sensors and all the resources through a common network, and the decision making is done at the rear, somewhere thousands of miles away. And especially when you go for advanced technology like BMD or other mission Shakti, it is not possible to control the whole mission from one place. So it is imperative that we have to network multiple resources and have a common decision making. And this is one of the main difference between the earlier technologies and the present technology, because of which we could achieve Mission Shakti. Of course, this I'm sure some of you might have heard earlier some of the wars fought by other countries. The battle was fought somewhere in Middle East, but the control rooms were in some other continents, and they were controlling all operations from somewhere far away, thousands of miles away from some other continent, because information from the battlefield was going to the control center. The decision is made, again the action was implemented through again network. Similarly, for this our mission also, we had to deploy multiple sensors across India, some in the southernmost tip, some are on the western side, some somewhere in the central India, and almost 10 to 12 locations were participating. All were geographically distributed, but yet the aim is only one, that we have to have this mission. So there are 2-3 major challenges in this mission. In fact, some of these are common for even BMD or for the other interception scenarios. Here, the challenge is to intercept a small body. Typically, a satellite is you can see the cross-sectional area of a satellite is not more than 1 square meter, and it is traveling at a velocity of almost close to 8 kilometers per second. Even if your interceptor is going at 2 kilometers per second, the relative velocity is almost more than 10 kilometers per second. Physically intercepting something which is traveling at such a high velocity and such a small body, this is a challenge. And other challenge is timing part. How do you make sure that you intercept? That means you have to reach where the satellite is there, and where the satellite comes at a later point, and accurately intercept. So for achieving this type of task, we have to work on many technologies. So one of the challenging is the prediction. Now, the satellite goes at very high velocity. In fact, approximately in less than 5 seconds, it passes over the country. And even if you use our interceptor lifts off and it has its own travel time. So when you start your actions, the satellite is nowhere in the horizon. It is somewhere in probably somewhere near the poles, or even far away. And you have to start your actions without seeing it, and based on the trajectory, based on the expected point which the satellite arrives at a later time, and you have to reach there thinking that the satellite is going to come at certain time t at that point. So here the challenge is the estimation. Now, any flying body, it encounters many forces, and then there are many disturbances. And so there could be some drift of the satellite. So if you think that, you're going to reach a point P, and whereas, there's a drift of few hundred meters, and here we are trying to hit physically with an object of 1 square meter cross section. And if you even forget about 100 meters, even a few meters also, you'll miss the target. So your prediction has to be accurate. And because what happens is, if your prediction is not accurate, then the errors are very high, and then you may not have capability to reach the object. So it's very important that you have very good algorithms which predicts the path and then future course of the object, so as to reach the particular selected point in a future time. Now this requires very very advanced algorithms. Basically, equations of motion, and then the flight dynamics of the objects. One is you need to know the dynamics of the satellite, and also you need to know the dynamics of your own interceptor. Because as I said that there are a number of variables in this one. One of the variables, if you talk about satellite could be the timing type of delays. And second thing is the disturbances, orbital drifts or orbital shifts. When you talk about our own interceptor, the time of launch. If the time is not accurate, then then you may just pass through before the satellite comes, or otherwise you reach after the satellite goes. So it's very important that you calculate exact time of launch, so that you reach within the kill zone. Of course, we have a wide kill window, but even to be within the kill window itself requires exact prediction. So your algorithms, start from one is, the dynamics of the path, the dynamics of the satellite, in which, how the satellite comes. And you should know the path of your interceptor also, the likely time it takes, and also cater for all the uncertainties. The uncertainties, thrust uncertainty. Suppose, you expect that your interceptor travels a certain velocity. Because of the variations in the thrust, it could be higher or lower. Then also, the winds also vary from time to time. So there could be some variation of winds, drag, higher drag, and there are almost 10 to 12 major variables which can play. So your algorithms or your planning software should cater for all these variables and uncertainties, and work out a suitable intercept algorithm. Then second important thing is the response time. One is response time is, of course, the launch, and second thing is onboard systems also. Because the velocity is very high, which requires your response of almost the order of microseconds. But today, those who are in engineering will understand that there are no systems which will respond to the microsystems type of times. Yes, there are some chips, or if you say that computer chips and all, where clock speeds are in the order of gigahertz and all, probably the clock frequency could be higher. But if you compute in a small software and a module, and then you have to run a cycle of operation, then it takes a certain time. So here the problem is at best we get a computation cycle of few milliseconds, whereas the requirement is of microseconds. And the other challenge is, still the computer systems are still okay. Now we have a mechanical systems. We have basically the rocket motor is a chemical product. The combustion has to take place, and then the gases has to expand. Then only we get the thrust. So we have chemicals which have to burn and get the things, and then we have certain electromechanical devices. Then you have some valves. Then you have some sensors which take their own time for detection and then processing of information. There are almost 10 to 12 such systems which have to work and compute their own subroutines. And when these all are integrated into the main software, then only get a response. So even if you take 5 milliseconds time for each system, then it becomes almost 50 to 60 milliseconds. Whereas the response we need is much faster. So how do you do? What do you do? So what we do is, we have a limitation that our systems can't respond to the type of demand which is required. So what we do is we go for extrapolation or prediction. Our algorithms are predictive in nature. So predicting that there's likely to be course of the object is in particular direction in particular magnitude, based on the trend line what is there, we extrapolate, and based on that one we start planning a priori. So this is very, very important because of these predictive algorithms and then the computation cycles, and then this is one of the most challenging and enabling technology for this mission. So basically what we require is, for a mission of this magnitude, we need algorithms which are very, very advanced and which works at a fastest possible cycle time. And second is the systems that also have to respond very quickly. And of course, the logics and the guidance and algorithm logics, and then the final interception algorithms. So these are the challenges. Now, other thing is, how do we intercept? Now, conventionally, we generally use, whenever we say that, like many of you might have seen in the movies and then some of the videos, how the interception, how the combat between aircraft, or how aircraft is brought down by a missile. In such cases, we use a warhead. You go close to the object, close to the aircraft, and initiate a warhead. So the fragments of the warhead go and neutralize the aircraft. So this is possible for relatively low velocity targets and big targets. So here the problem is, when you go for a very, very small targets are very small cross section area. One is that velocities are very high, so you may or may not be able to go close enough for inflict the damage. Second thing is, when the warhead is initiated, fraction of the fragments go and impact. Whether they will neutralize or not is a big question mark. So today, with the advent of new technologies, we are working on what we call hit to kill technologies. That means physically go and hit the target. By doing so, whatever kinetic energy or whatever momentum we have, this momentum gets transferred in neutralization of the target. So because in this case, because both the objects are traveling at very, very high velocity, even the small impact is good enough to have a huge momentum transfer and then neutralize. So we planned for this mission with hit to kill technologies using one of the BMD interceptors. But the missile itself is not adequate for this mission. You need many, many more resources. First is detection of the satellite. You need first some sensors to know, though in case of satellite, roughly likely path of the satellite. But as I said, that because of the drifts that take place, there could be some deviation in the trajectory. So here, since we are looking for a very, very fine control, in the sense that we can't afford to have even 1 meter dispersion, 1 meter deviation from the target. So we would like to have minimal drift. So what we have is, we have our own sensors to track the satellite. So here the requirement is, you need some radars or other optical sensors to detect the satellite. Now, conventionally, the radars are the sensors which are used by our defense services, be it be Air Force, Army, or Navy. They have only few hundred kilometers range. In this case, and generally they detect aircraft which is quite huge in size. Whereas in this case, the object is very small, and you have to detect it very, very farthest possible range, because the velocity is very high. It is almost 8 kilometers per second. Then even if you detect at 800 kilometers, that means you have only 100 seconds reaction time for you to compute all operations. I'll tell you what all operations we need to do. So first and foremost requirement is to get information that yes, the object is at so-and-so place, and then it is coming as per the path, and to track the path of the object, so that you compute your solution, which is the right place and right time to intercept. So here the challenge is to have a sensor which can give you very, very long range, and will be able to track a small object. It's something like, if a bigger object, you'll be able to track at a larger distance. But if the object's size becomes smaller, the limitations also come in. So first is to have, and one such sensor will not do. We need multiple sensors, because as I said, that for our mission itself, we had to deploy many sensors across, because first one sensor detects, and then after a few seconds it will lose, then second sensor tracks, and then pass the information like that. So first and foremost is, yes, the sensors to detect, and many of them to cover the path and then give the information. And the second is what we call the C4I system, which is the nerve center. Now what happens is, the information is there, there's an object which is tracked. Now the object information has come to your control center. Now based on the present position, now we have to extrapolate after which time the object is likely to come into your kill zone. So for this one, the centralized control center has to get the information, process, and then work out the intercept solution. Now I said a few minute before that you have multiple sensors. Now what happens? There are almost 10 sensors. The 10 radars giving information. Now all of them correspond to same one particular object. It should not happen that the data from 10 sensors is taken as 10 different targets and then we work on a different solutions and all. So one of the most important thing is the association. Even if there are 10 to 15 sensors, radar or optical sensors tracking, the information of all 15 should be associated, and then control center should know that yes, it is one object which is coming. If he says that then 10 objects coming because of data from multiple sensors, then you will lose. So it's very important that the association should take place. And of course, second thing is classification. There are certain parameters through which we classify. Generally, if it is a satellite, then satellite travels very, very high. And the velocities are very high and altitude is very high. If it is aircraft, generally it confines to less than 25 to 20 kilometers altitude. And the velocities are, it goes horizontal. And if it is a missile, then it goes vertically up. And then there are different characteristics of each object. So accordingly it classifies. Then when he knows that there is one object coming in this direction, then the nerve center should identify an optimum intercept solution. So that when that object moves after a certain time, the interceptor is launched in such a way that interceptor also reaches in space a particular area, what we call a kill zone. It is something like our capability, with whatever energy we have, we'll be able to engage in probably, a couple of hundred square kilometers. Beyond that one, we won't be able to reach, or otherwise, the target passes away. So the intercept solution is worked out by the nerve center, and then it issues a command for liftoff. Now, this is second important activity, the main nerve center. And third important thing is the communication. Now, we have around 10 to 15 different agencies participating in this mission. Now, all have to be in the same common time frame. Suppose someone says that, okay, the object has passed at so-and-so time. And if my time and then the particular census time is not same, that I am thinking that, object, when he says, particular time t, I may be at t plus t dash. So this will lead to addition or reduction of time, and then ultimately you'll miss. So it's very important that we all are in the same time synchronization mode. That means the clocks of all the sensors have to be aligned to the order of more than microseconds. Of course, GPS and all gives order of microseconds, and then we found that in certain scenarios even this become critical. So we had to rely on a higher clock speeds. And second thing is the communication delays. We have to cater for this communication delays. What happens is, as you all know, when you use terrestrial communication delay, it takes approximately less than 100 milliseconds time. When you use satellite communication, it takes probably, depending on number of hours, anywhere between 150 to probably 250, 300 milliseconds and all. So with the data which I get, which corresponds to the position of 200 or 300 milliseconds earlier, I have to extrapolate to the present time and compute a solution, and then again further extrapolate to the future, so that my final intercept solution takes place. So these are the few, very, very few, though appear primitive, but quite challenging for us to work on these technologies. And the second thing is the data links. Now I said that there could be some drifts of the object when it comes. Now what happens if there is a drift? We are thinking that interceptor is already lifted off, thinking that the object will be at so-and-so location, but there is a significant drift. So finally, when the final onboard sensor opens up, it finds that the drift is quite a bit, and then missile may or may not be able to engage the target. So what we do is the information of the target, as we get during the flight of interceptor also, we pass it through data link. So to have a data link, if my engagement zone is a couple of hundred of kilometers, then I need to have a data link also to support. So multiple data links and all working in the same zone. So these are the few enabling technologies which we had to work on for this mission. Now, of course, we had made a good progress. That way, DRDO continues to work on these advanced technologies, and with experience gained in many areas, starting from aircraft, missiles, materials, naval systems, and it literally DRDO works on every domain of technology. And the expertise gained in different domains are used and then customized for a particular mission. So, for example, I was telling even for the mission Shakti also, we had launchers, which are something like semi-combat vehicles type of thing, and then we had a missile which is an airframe using all the aerodynamics. Then we had a propulsion, and we have control guidance. You name any technology or domain of engineering that is applied in these missions. So that way, I think with whatever we gained in the previous years, and especially since we had successful trials in the BMD technologies, then adaptation became quite easier. And then, of course, we had to work on some of the new technologies to make this mission possible. So with this background and then our know-how about the technologies, what DRDO has developed. In 2016, DRDO got an opportunity in the sense that Honorable Prime Minister requested our chairman DRDO if we could plan for a mission like this one. If someone says that you have to hit a satellite which is traveling at very high velocity at 300 kilometers altitude, it's not an easy thing. But I think that way DRDO and especially our chairman took a very challenging task. This gave a commitment that yes, we will do it. And the requirement was we have to do this trial within 2 years, because this mission is one of the challenging mission, and to be held at utmost maintaining utmost secrecy, and this mission can't be done in an open domain. And if you drag more time, then again information leaks out and all. The challenge was to have this mission in 2 years time, and many new technologies were there. So then we started working on the configuration of the vehicle. So basically, what does this mean? This mission means we have to work on the three main areas. One is realizing the interceptor itself. The missile has to be a missile or interceptor has to be made, which has to travel hundreds of kilometers with whatever velocity, and then reach the altitude of the object, that is satellite, and also have sufficient velocity to cause damage through momentum transfer. Second is, of course, satellite itself, the target itself. And the third is, I said that, the weapon system elements. That means the sensors, the communication, the data links, and then C4I systems. There are, network of systems which are to be established in a distributed area, because spanning in an area of almost hundreds of square kilometers. So these are the three elements. Then we started having the mission planning. And since 2 years is very short, we decided to distribute the work so that, because otherwise, typically what happens is in a new project, if you have to develop, it takes anywhere between 4 to 5 years. Earlier, it used to take much longer time, because now we have maturity of technologies in DRDO. So that way, quickly we are able to harness and then configure to the particular mission. So that way, even then, starting from scratch, it takes between 4 to 5 years. So what we decided was, first, we'll distribute the work with the various work centers. It helps in 2-3 ways. Because we are distributing the work, many people can work for it, and then that way, effective time can be brought out. Second is that information secrecy also. If you all work for one project, everyone knows what we are working for. When the work is distributed among many people, then they know about that small module of the work, what they are doing. The global picture is not available to everyone. That way, we thought we can also meet the objective of secrecy. But again, here the problem is, when 50 people work or work on a small modules, what happens if when you integrate, they don't match? So the integration plays a very important role. So the mission planning, work planning, how you plan the work, and then very precisely you have to identify the modules, and with the correct interfaces you have to hand over, so that tomorrow when they come back with these modules, you are able to integrate them, and then you get the desired thing. It has its own challenges, but we had no other way than going for this one. And coming to interceptor size, we borrowed one of the BMD, broad BMD interceptor with, of course, certain changes has to be made. And of course, since our BMD typically, our interception takes place at less than 200 kilometers altitude. Here in this case, we need to reach much higher altitude. So we need higher propulsion. So we had to realize the two new stages of propulsion through one of the other sister project, and we married these systems so that we get interceptor which can have a sufficient energy at 400 to 500 kilometers altitude so as to inflict the damage. Now, of course, when we integrate different systems and all, the size changes, the aerodynamics changes. So we had to go for a fresh aerodynamic study of the whole missile and integration of all the technologies. So this took significant effort, and the control guidance algorithms had to be reworked and all. And finally, we realized a new interceptor, the mission Shakti, which is around close to 20 tons weight and then 13 odd meters long. It is a 3-stage vehicle with a 2 stages of propulsion, which takes to certain altitude, and then finally the kill vehicle, which goes and impacts the incoming target. Then parallelly, we started working on looking for the target satellite also. And there also we had a lot of changes, challenges, because typically the satellites, even in LEO, they fly at a higher altitude. The altitude is anywhere above 300 to 400 kilometers altitude. But our requirement is we wanted to have interception at a lowest possible altitude, so that we don't cause any collateral damage to other objects. But here the challenge is, if you come to the lower altitude, the life of the satellites becomes very short. So it starts, because of gravitational force, it keeps pulling down to Earth, and then since you use propellants to correct the orbit, so within 3-4 months, then you lose the satellite. Now, one side we are going for a mission, which is such a challenging mission. First time we are going without actually flying any earlier occasions. And first time itself, you have to be very sure that not only you reach, and also, sorry for the inconvenience. I think some disturbance at home. Not only that. So not only you go for the mission for the first time, and then ensure that we have a full interception. So this becomes a very critical that timelines were very short, because the moment the satellite is launched, we have to do the mission within 2 to 3 months time. Otherwise, we lose the satellite. So this puts more pressure on the program team that you have to have it within the time. So as such, 2 years is very short. And then first few months goes in the mission planning and all. Then again, work planning, distribution and all, integration and all. That way it became very critical. But one good thing about this one is, now today our Honorable Prime Minister says that, Atmanirbhar. That means you have to be self-sufficient. That way, I think we are very fortunate that our mission also, since we are working on all indigenous technologies with everything realized in-house. So that way we were confident that yes, we'll be able to realize. But again, challenges for many. I said that, response times of the systems are not as we expect. Because your computation demands very, very high response time, whereas your physical systems don't give. But we have to overcome this with the advanced algorithms. Similarly, everywhere. Now, one simple example is the launcher. Typically, the launcher which carries the interceptor and then launches the interceptor, it takes anywhere around 2 to 3 years realization. We don't have these type of times. And so we used one of the existing ones with the modifications, redesign of the launcher. Now, 3 to 4 months before the mission, we found that the missile has to be a certain altitude. Otherwise, there could be back pressure and it likely to impair the interceptor. So time was not there. So what we did was, again, some innovative idea that why not we raise the entire launcher up by 1 meter. That way, I think we had to work on each and every element, and then work on that one to achieve this goal. So finally, it was decided based on our interceptor side. We decided to go ahead with hit to kill technologies using a imaging infrared seeker at an altitude around 300 kilometers. Then another issue, we had, everything was a challenge during this mission. Secondly, I was talking about the object. Typically, the satellites come over the same area in around 12 to 15 days, because taking the Earth rotation of close to 30 odd degrees and all. So if today the satellite comes over an area, for the satellite to come in the same area, it takes around 12 to 15 days. But mission of this type, we cannot afford to have this type of delay, because the moment you try for the mission, and then if for some reason there's a hold up, and then it will be known to everyone, and then mission may not take place. So we wanted revisit time almost every day. Then again, this was worked out, and then one SSPO orbit, sun synchronous polar orbit at 285 kilometers altitude appeared to be ideal. In which we had two passes over our zone, one in a day and one in a night. So this was finally worked out, and then interceptor was worked out. We went for a mission. Now, planning for the mission, again, some of you who are aware of our missile launches, which take place from eastern. Typically, we launch our missiles on the eastern India, starting from Balasore into the sea, because we need a clear range safety corridor. Because the burnt motors, they impact into the sea. So we need to have a clear safety zone. In this case, we are requiring almost 2,000 kilometers of safety zone. So get a clearance. Safety zone means you have to literally vacate everyone, all the aircraft, all the ships, and everyone to be away from this zone, so that even if our systems fall into the sea, no one gets impacted. The problem was when we went for the mission, post Balakot, the Pakistan has closed its airspace, and all the international traffic was coming through this area. So even to get a small window was extremely difficult. So our timelines were getting squeezed. Window was a problem, and our corridors were so narrow that you go to the left, then you land somewhere in Indonesia. You go to the right, you land in Sri Lanka. So we have very narrow corridor. Within the same narrow corridor, we should look for a interception zone where the satellite also comes into the kill zone, and then our interceptor reaches and then neutralize the target. So this is one of the challenge on the mission planning and then mission safety wise. And of course, management wise, since the timelines are very short, the scientists kept on working almost 15 to 18 hours a day, because unlike other projects here, the timelines are already fixed. If you don't have the mission by certain time, then a satellite will not be available and we lose the satellite. So it's very important that we have to meet the deadline. So time pressure was there. So people were working almost day in and day out, and all managing the stress, managing the pressure, and then the curiosity. All the scientific minds, scientific or engineering minds, we go through the logic. Everything we question, why this way, why not that way? Because there's a difference between other disciplines and then science and technology is that logic, ability to apply logic, the whatever called Boolean, why this way, why not that way, and all. So everyone started asking, what is that we are doing? Because no one was told what we are doing, and everyone had this doubt, there's something going on fishy, and then no one is getting a clear picture. So dealing with the people, dealing with the stress and managing this other thing, and then finally, we went for the mission. Here, I'll just talk about a few of many technology, how we had to work on each and every technology. For example, typically for our final kill vehicle, when you use liquid propellants, you get thrust by liquid propellants. That means we have a liquid propellants. We open a valve, propellants flow. Combustion takes place in a small motor or a thruster, and then the reaction through a nozzle gives you that thrust. So this is how you require the force at a very, very high altitude. Now, typically, some of you who are working in this area, any electromagnetic system, it takes a minimum response from the moment you give a command. Then the electrical signal energizing a magnet or whatever system you have, and then opening a valve, and then allowing the propeller. It takes minimum 60 to 70 milliseconds. Now, if you see our cycle of operations, suppose, in fact, I was telling that we start with the predictive algorithms, thinking that I will have interception at point P, where the object is going to come, and I'll also reach at point P in time T. Now I find that when my terminal sensor, when the seeker opens up, that I am not at P, but I am at P dash. The P dash could be probably P plus 200 meters and with a difference of 2 to 300 meters. Now the onboard sensor has to say that detect the deviation. The sensor has to find that there is a deviation. The information of the sensor comes to the onboard computer. The onboard computer compares where the difference between P to P dash. Onboard computer has to think that now this is supposed to be P, but where is it P dash? So it has to calculate the difference of the PP difference P dash. Now the computer has also to compute to correct this difference between P to P dash. What type of force is required because of because the force is applied at some corner, then with momentum and all. So once it computes, then he says that okay, I need a force of F from at so and so place. Then it gives a command, electrical command to the valve that okay, allow this much of propellants to flow. The valve opens. The pressurized propellants, in fact, in this case, two propellants, they have to flow through whatever pipelines and all, come to the combustion chamber. The chemicals have to burn and then generate a pressure. The pressure is expanded through nozzle, and then only you get this thrust. So from the time you find the deviation and to the time you actually get the thrust, there is anywhere between definitely more than normally 100 milliseconds. Now here our requirement is the relative velocity is almost 11 to 12 kilometers per second. Here we would like to go to the center of the object. Even if it's a matter of few centimeters, means your response has to be in microseconds time. You can compute 11 or 12 kilometers per second, and then if you come to centimeters, then what type of time? You need almost microseconds type of reaction time. Here the challenge, you have systems which are giving milliseconds response time, and whereas your system demands that you need microseconds type of reaction time. So everywhere, we have to work on the technologies, and we've gone through each and every element. For example, I was telling you the valve. Typically a valve takes the best of valve takes around 60 to 70 milliseconds to open. Then we have to redesign with with a higher rating and all to operate it in less than 10 milliseconds. So this has made this enabled our final mission. So like this, every element we have. And second thing is we have this thrust. Generally, typically what happens is once you fire a motor, you forget about it. Whereas in this case is a continuous guidance. I need number of pulses. And these pulses I want as less as maybe 20 odd milliseconds pulses. Now, if I give it command now, the actual the effect will come after 60, 70 milliseconds. I want only 20 milliseconds. That effect I'll get after 70 milliseconds again. So what I have to do is, before I actually get the requirement, I have to issue the pulse and also withdraw the pulse, so that the effect comes after 70 milliseconds. So this means my algorithms has to compute a priori and then work out based on the trend. And of course, we had to have our own filters. If you don't have filter, what happens is continuous operation in both sides, across the equilibrium. Then no time you consume all the propellants. And the second is our onboard sensor. Onboard sensor, it is like an eye. What happens if you look into the sky in the night? You have thousands of stars, thousands of objects. Similarly, our sensor also, when it opens into the sky, when it looks into the sky, it sees all planets, the stars and all. Among all of them is your object, which is a very, very small. As such, in everything is subpixel, small dots, and among this one, this is also one dot is there. And at best, you'll be able to detect at probably less than 200 kilo, or maybe order of 200 kilometers. So that means maybe you'll have around 15 to 20 seconds total time in which you should have interception. Now, one side you find that 1,000 dots in your screen, among which there's one dot. You don't know which one is actual your object. So your sensor algorithms also, the signal processing, whatever data you get, the signal processing, that should take care of the discrimination. You have to identify among these 1,000 dots which dot is the one that corresponds to your actual target. So this becomes possible, after a certain time, because as it comes closer, the object grows. When you see the aircraft in the sky, initially at the far off it is small, and as it comes closer it becomes. Similarly, an object also, as it comes closer it becomes slightly bigger, and then with this change in the growth, you'll be able to identify. And again, a lot of disturbance. If it's daytime, you have a thermal effects, and then if it is daytime, then you have a sun effects of sun and all. So you need to have a lot of filters to filter out all the noise and then come to the station. So the challenge is to have a sensor to detect at a very long range, and also to get a track confidence, or otherwise with assured detection at the earliest possible instant. So this is another very, very challenging technology, because and second thing is, if you go for uncooled type of seeker, you get range limited. So again, it have its own cooling system. You have to maintain temperature almost minus 200 degrees, then only you get a further range and all. To have onboard these systems, to maintain temperature at such a low temperature, and then have these algorithms working in real time, this is a major challenge. That way, I think we had many more challenges as guidance and control algorithms, which are the most challenging thing in this mission. Then the seeker to detect at a farther range and still give you sufficient reaction time to engage with such a high velocity objects. And then the control systems, the liquid based control system, reaction control system, which allows the maneuverability of the object, so that you go and have a physical impact. And then of course ground, the computation, time to launch. And these all are many technologies which were used for this mission. And finally, on 27th March, based on the data from our sensors, and then the mission dynamics, then we had conducted the mission at approximately 11 o'clock in the morning. The first stage of rocket motor took to altitude of around 50 odd kilometers. Then the second stage took us to altitude of more than 100 odd kilometers. And then finally, our kill vehicle detected at close to 200. I'm deliberately not giving exact figures. 200 kilometers, and then the target was engaged with a physical impact at 283 kilometers altitude. And we had multiple sensors which are tracking the missions, and then finally the target got neutralized. So I think this is one of the very live example where as a nation we all could prove to the world with our own indigenous technologies. If you see in this one, most of the things, because no one supports us for this type of technologies. Even for BMD also, we had certain instances where someone who was willing to supply initially, also later backed up because of international pressures, and we had to develop everything on our own. And especially for technologies had to have satellite interception, and that too is available to very, very few countries. In fact, India became fourth country to have this technology. So we had to realize everything through indigenous technologies. That way, I think DRDO had a good beginning in these areas, and we could configure them, and then to suit the requirements. And wherever required, we had to work on a new algorithms and technologies. Finally, we could make this mission. I think it's a matter of pride for all Indians that today our nation stands among the other three in the world to have demonstrated this technology. It is very, very important, because not only that one has the technology, that one has to let others know also that yes, we have this capability, which is what is called deterrence. We don't do anything, but others knowing itself that yes, they have this technology will keep them away from any of the mischief. So that is very important, and we are happy that we are also working in line of the self-sustained growth in technologies, and what our Honorable Prime Minister says today, that self-reliance and then made in India. So for this mission, along with our DRDO team, we had many industries working with us. We have involved almost close to 50 odd industries for relation of systems and all, and then they all realized the systems. The quality is very important because the first mission itself has to be success, and you may not get a chance for a second mission. So a lot of emphasis was given on quality and reliability, and then finally we could achieve. I think this is one of the great achievement for the nation, and rightly so. Honorable Prime Minister, he came on the media and addressed the nation, highlighting the achievement. And subsequently, in interaction, he emphasized that this mission should be inspiration to the future generations also, especially the children and the students who are pursuing science and technology, so that they also have the motivation, and then they get a confidence that yes, working on our own technologies, we can achieve whatever is required. So this is a message he wanted us to carry to everyone, to inspire every child in the school, every student in the college, that yes, as a nation, we all can do it, and we'll become stronger only when we become stronger in technology. I think that way I thank Vigyan Bharati, who take initiative in promoting science and technology, and encourage students to participate in science and technology missions. I once again thank Dr. Shastri Garu and Vigyan Bharati for this opportunity, and Jai Hind.